Hello, I'm Daniel. I'm here from New York, where I work for a company called Bandwagon, and I'm excited today to be talking to you about one of my favorite things to work on, which I'm going to call microclients. A lot has been said and written lately about microservice architecture, a particular style of building applications out of many constituent parts instead of as a single monolithic whole. Microclients are what I'm calling the other end of these services, the glue that makes a microservice architecture possible, the client code that consumes the microservices. Just as there has been some question as to what makes a service a micro one, we'll look to characterize their ideal clients as micro in a meaningful way. So that discussion about microservices that I mentioned was in part kicked off in March by an article by Martin Fowler and James Lewis of ThoughtWorks, appropriately called Microservices. While it didn't coin the term, it helped kick off some discussion and went forward and hazarded a definition of it as a certain architectural style, which is characterized by a single application as a group of services. This is key. We're not talking about multiple applications that talk to each other, but something that is conceptually whole, but made up of many constituent parts, which happen to be separate programs, possibly running on separate machines. And that the communication between these parts is lightweight, which in practice almost always means JSON over HTTP. And the different components are defined by their business capabilities, not necessarily their technical ones. A component with capabilities that are distinct in content, not form, is something that should be pulled out as a microservice. It's not just a matter of accessing the technical capabilities of another machine. It's a matter of accessing knowledge embedded in functionality implemented in another isolated program. Lastly, these services are not centrally managed. There's no implied orchestration layer. There's no service definition to fetch and process in order to interact with them. Here's a visual published with Fowler and Lewis's article, contrasting microservice approach on the right with the monolithic approach on the left, for those that are more visually oriented. Now that we've established what microservices are, let's see why we might want to leverage them. The first reason, I think, is developer ownership that facilitates maintainability and flexibility. Apparently at Amazon, working groups on small services were governed by a you build it, you run it mantra that kept the people who knew the code best close to its deployment and aware of the needs that it was confronting, the stresses being placed on it, etc. This is consistent with the emergence of the discipline that is being called DevOps, or developers and operations people, starting to overlap and share responsibilities as opposed to the sort of throw-it-over-the-wall model of larger applications, larger monolithic applications. The next is sort of enforcing the single responsibility principle at the architectural level, the idea of building programs that do one thing and do it well, rather than this huge monolith that may do some things okay and some things not so great. Lastly, and most excitingly, I think, the microservice architecture approach enables a polyglot orientation, multiple language, multiple frameworks, multiple tools, all under what we've characterized as a single conceptual application. This is particularly exciting here because I think it's one of the things that makes conferences like this more relevant and more useful to more people, because it means that the different technologies and different languages can still be used in a larger project without that much overhead. One question that came out of the whole coinage of microservices as a term is the idea that it's not a new thing, that service-oriented architecture has been around a long time, also called SOA, and that it is also a term to describe a whole made out of many constituent application parts. However, this descriptor gained prominence when technologies like XML and WSDL were more popular and, fairly or not, has come to be associated with them and the types of systems which they tended to produce, which are distinct from the ones that the microservice style has tended to produce. So first, there's the lightweight deployment. I mentioned this before, the idea that developers and small teams could deploy these microservices that are part of a larger application and have a greater sense of ownership and involvement in their ongoing release and maintenance. The next is the break with centralized governments. A lot of the technology that is associated with SOA as a term relies on centralized definitions for how components communicate. There's also an important asymmetry between microservices and a host application with which they communicate. At some point, the different domains that are being isolated in different microservices need to be brought together into a larger context by a program that knows how to handle them and knows how to put them in conversation. This is distinct from a situation where you have multiple large applications talking to each other on a more level sort of playing field. The next is that the underlying technologies tend to be more web-friendly or web-native. Again, JSON over HTTP. This contributes to making it easier. This helps make it easier for many developers, regardless of background or language knowledge, to understand what the service is providing. You can open it in a web browser, see what it says. JSON is pretty human readable. All of this can sort of be summed up in this catchphrase, smart endpoints and dumb pipes. Service-oriented architecture style systems implemented business logic through message passing systems that understood what that data meant. They were tightly coupled. They relied on centralized governments for schema definitions. Those pipes were smart. We're looking at microservices as something where the pipes are dumb and the endpoints are smart, which we'll get to a bit in a moment. So what are the implications this has for microclients, the things we're here to actually talk about? They should also be lightweight to avoid canceling out all of the benefits of microservices. If implementing the client end of extracting a component of an application into its own service has a high overhead, there's no reason to do it. Additionally, this client code has to supply some of the structure that had been taken care of by having centralized definitions in older models like the service-oriented architecture one that we were discussing. And that these clients, like their service counterparts, work best when based around web-native principles. Which sort of brings me to the big thesis for this talk, which is that the microservice and the micro in both the service and the clients refer to minimizing the cognitive overhead of having part of an application extracted into an autonomous component. The reason this is important is because it leaves more room to think about your program by reducing the additional stuff you have to hold in your head as you go, the cognitive overhead, involved in communicating with an external service. On the server end, keeping the exposed resource narrow in scope helps too. This again contrasts with the more elaborate inter-application communication that we're contrasting between the old sort of SOA paradigm and this possibly emergent microservice one. But this also implies confronting certain trade-offs. If we can't efficiently manage the client end of the microservice architecture approach, then adopting that approach may turn out to be more trouble than it is worth. So we have to find ways to balance those concerns. Even if the server providing the microservice is super lean and simple, if the client that consumes it requires too much effort on behalf of the programmers working on the host application, it won't be worth adopting. So let's give building our own little microclient a shot. The examples for this are in Ruby. I think that the general principle should be easy enough to follow, and many people know HTTP anyway. So here we have a basic class that we have set up that has access to a connection instance that points to a service. It creates that connection using a gem called Faraday. Faraday is a great Ruby library that can be used as the basis HTTP client to build a service-specific HTTP client. It exposes a simple idiomatic interface for getting at data on a remote server. So why use something like Faraday and bring in more stuff when we're trying to lower our overhead instead of using the standard library in Ruby for HTTP? Well, the libraries that implement the basic functions for HTTP clients upon which service-specific clients can be built handle things like authentication and logging that we shouldn't have to reinvent in order to interact with our microservice because we're trying to minimize the overhead of doing so. Additionally, they provide tools for content negotiation and result transformation, which, as we'll look at later, is important in some of the new ideas about how to organize microservice-type architectures. So let's start with getting to extracting some capability into a service. Here we have a silly little utility to get the number in the Fibonacci sequence at a particular index in our math utility class. So let's go back to our little API client. We've already put the service to talk to the server together, so now we just have to get our Fibonacci URL and pass the index as a parameter, and we're done. Well, not quite, because, and this is true in many libraries, the object we would get back from that get is a larger response object that includes information like headers, status codes, etc., but we just want the body. The reason for that is if we're trying to reproduce the interface that we previously had, we want to minimize the extent to which the fact that it now lives on another program or another machine, we want to minimize the extent to which that leaks out. So our math utility can now grab fib at index using our client method. In this example, we've now added the capability to math utility to pick up an instance of our client. But this is crucial. Let's suppose the body that comes back from the HTTP request to the service is a hash with a key fib that is actually the number that we want. Now we need to embed that knowledge in this code in order to replicate the interface that we had for math utility before. This is a problem. Where to put this information requires certain compromises, and we'll see this happening again and again, the extent to which we need to embed knowledge about the service in the host environment. Also, there was a bit of a mistake in that last slide. The client here just gets sort of generated by magic. If it doesn't exist, we just create a new one. We should probably pass in an instance of the client to our math utility class. This is important for things like testing, having multiple connections to the client. If it's pointed at multiple services, who knows? But it is, again, one of these trade-offs, because we are now exposing the fact to the host environment that this class now uses a client to talk to a remote service. We can mitigate that by making it optional, and so we can still have our old interface and simply ignore this. But again, there's this problem of leakage. So now let's move on to another way to integrate remote services, which is having models that talk to them. So here's our smart number model. We initialize it with a property necessary to perform requests associated with this instance. Now, this is often an identifier, like an ID for a database record, but in this case it isn't, and it doesn't always have to be. Maybe we already have the resource, like a user or something, and we don't need to go get it, but just perform some expensive computation on it or evaluate some unique property of it. Maybe the service we're extracting really is really small, like a couple of math problems. And again, we initialize our smart number not just with the number that it is, but with an instance of the client for the reasons mentioned above. And again, this introduces some of that exposure of the fact that we're working with a microservice into the host environment. So now we've got our smart number, and let's say for this purpose we are moving the knowledge about the payload result into the client so the model doesn't have to know about its secret life as an interface to another program. And so our fib@index method just talks to the client and gets our number. We can also have other numbery stuff that talks to our math service, like whether it's prime and whether it's one of our favorites. But that's also a trade-off, but it's one we can mitigate with a different design choice. So all we get back for these is a number or maybe a Boolean. But that's also a trade-off, but one that we can mitigate with a different design choice. We could embed the knowledge of the structure of the response in our model class here and maintain the option to get the raw response object back. Now, this is a compromise between making the fact that an external service is here and making it visible, and that we want it to be invisible, and having the necessary access to interact with the mechanisms that the integration is based on. Now, just another design point that will be relevant later. We don't want to write a bunch of redundant methods for each API call, so we can make sort of generic ones like this get method that composes a URL to get information about our number. And we can use that to create other ones to build methods that expose access to resources based on knowledge about the service passed to the client. So we tell smart number about prime, and we can get our prime request. So what have we gotten for all of this trouble here? And this is where I think microclients have the potential to really shine. There is an opportunity to integrate external services in ways that feel natural and intuitive for a particular programming environment. At the top, we have a Ruby idiomatic way to pluck numbers based on a Boolean property out of a list of them. Now we can do the same thing in the same way with our slightly smarter numbers that know whether or not they are prime. This is what I think we should be designing for, and this is what I think sort of defines microclients. The ability to slip into larger host programs, expose additional functionality that lives in another program or another machine without disrupting the idioms and conventions that that host application is based on, and design decisions that the host application is based on. However, this smooth, unobtrusive integration only works while things are working as expected, which is also why we need to focus on the most important idiom of all, error handling. On the server side of the microservice architecture equation, things are sort of simple. If there's a bad request, we're going to eventually send an error response. If there's an exception when we're executing the request, we're eventually going to send an error response. The end result is basically the same. From the client perspective, we need to decide what we're going to do. Do we throw an exception that's going to bubble up and maybe crash the program? Do we convert something to an error that's suitable for end users? We're not sure whether the service we're integrating with is inside or outside of our larger application, so there's a question of how to treat errors that come from it. In order to get at what we should do, let's take a look back at our pre-extraction situation. So this is something that you would never do and doesn't make sense and only causes damage. But this is what happens when response bodies from API requests are returned. We just get maybe a hash or some sort of object with some data about an error that happened. Obviously, you would never create that situation yourself, so why would you allow it to happen simply because you're integrating a remote service? In the case we just described, we don't know whether the error has a user-suitable message, what information it has about the server's error, if it's our error. Since it's not an actual exception, we can't handle it using normal exception handling. We are left with forking execution pathways because our insane error handling plan leaked out and forced us to change how we handle things when things go wrong. This can also happen if you return response bodies from this microservice through this microclient as error response bodies. That's not even the worst possible solution. This could be done. We could fail to get our number and just return nothing, and then if we proceed as though there had been no errors, we get Rubyist's favorite error, undefined method for nil class, and now we have no information about what actually went wrong. So, principles for error handling for microclients. Swallowing errors loses information, so we should not do that, because we need that information to prevent subsequent errors. However, if what we're talking about is one application that happens to have things extracted as microservices, we should still treat it as an exceptional case, a case where things are broken. That is, the application should blow up as a result of the fact that our code didn't work the way we expected. Remember, it's about business logic defining the different spheres in which services operate, not the infrastructural fact that something happens to be being performed on another machine. So we want to abstract away that difference and say, this is still an exceptional case. We still need to, let everyone know that something is not as it should be. But we don't want to necessarily do this in a way that surfaces the fact that we're communicating with remote systems. Remember, we're trying to do this in a way that sort of hides the fact that we are. So here's one way we could get at handling this. Suppose we create a special exception class, possibly a subclass of an exception class specific to our math utility, that we re-raise with a more informative error message about what went wrong when we were trying to do our little Fibonacci math. We'll also log the error that from the actual work part, so we know what went on. We could also maybe attach more information to the error message, but we've raised an error that is appropriate to what the class was trying to do. This is the exact same thing with our service examples or our service interaction swapped in. Maybe we attach more information to the error about the services, about what went wrong with the service, but we've also logged it. Maybe we can alert an external exception tracking tool, but we've remained the pattern of not compromising our original design decision just because we happen to be integrating with a remote service in order to accomplish our goals. Looking at error handling, I think, is interesting because it shows us that we're dealing with a borderline case for what is inside and what is outside of what we want to consider our application. For example, if you were talking to a remote service that was not your own, that somebody else ran, that is not micro, would you crash if every time it went offline or you couldn't reach it. If your payment gateway suddenly stopped working, should that blow up your application? Probably not. For better or worse, service outages or failures on behalf of somebody else's application are things that happen and can't be treated as exceptional or unexpected states. They are states we have to anticipate and have ways of dealing with. However, when our application, remember, we're talking about one application that just happens to have some things pulled out as microservices. When our application doesn't work, we need to be throwing in it should blow up because we need to know about it. So how do we avoid that whole error situation to begin with? So here are some tips that I think will help with that. One is to have tests. These tests should be able to be run in isolation. This is very important. Building client libraries that only work when they're pointed at an instance, a running instance of the service is extremely difficult to maintain because there can be inconsistent behavior. Different people's environments when they are running the local version of the service that they are talking to could be not the same. It's critical for having consistent behavior for the tests for the client library that they be run without pointing at an instance of the service. Another interesting compromise that I think can be made is that the client libraries can serve as a sort of acceptance test or living documentation for the service they interact with. This isn't necessarily an optimal situation, but again, we're talking about efficiency for the sake of lowering the overhead for introducing a new component to a larger application as a service. A couple of tips about releasing and deploying your microservice library, microclient libraries. You should make them standalone libraries. It's a way to insulate changes in the service it's a way to insulate the host application from changes in the service because you can adjust you can change the client library. It's also, right, we're only giving the client one reason to change. The host application should not have to change because the details of the service implementation changed. It's also a familiar pattern because of the way larger services just build SDKs and client libraries, which allows us to work in ways we are familiar with. We should also enforce compatibility between versions of our service and our client. There's many ways to move version information around, but whatever one you pick, we should refuse to have the client code start up at all if it's talking to something that it doesn't know about or is unexpected. The other way to deal with this, which larger services do, is to always support, or to support to the extent possible, backwards compatible clients by having the client send a version and have the service respond with the appropriate behavior for that version of the client. This is a little non-micro, so we'll leave that to macro services. So those are some microservice things. I think an interesting thing about this whole discussion is that a possible re-centralizing trend is taking place. We discussed in a couple points the sort of challenge of deciding where to embed information about a service if we don't have centralized definitions for that service. There are some ideas that are emerging about ways to embed information about services in the services themselves. This is what is described sometimes as hypermedia. And it may have implications for how we have defined microclients, particularly the problem of embedding details embedding details in ways we might not be comfortable with. One of these emerging protocols is called JSON API. It has its own media type. It defines means of extracting information from response payloads from services in order for the host application to understand what they mean. One of the things I think is interesting is that the introduction to the project that they present indicates that it is also being driven by this idea that we can focus on our application by removing the focus on the way that we have to interact with services. Remember, we want the pipes to be dumb. We don't want to have to think about them. This is what a JSON API payload looks like. The links element is what is key here. It's a schema that can be used to define additional action. The schema can also be used to define additional actions, like our prime example that we had earlier, where we said, this is our get method. We can pass it any old action, and we know how to transform that into a URL that we can make a request for. those actions can be defined by the can be defined in the payload that the service responds with, in addition to knowing how to look up people, for example. Another very similar project is HAL, Hypertext Application Language. It also has its own content type, and it also describes itself in terms of being a way to focus on building applications rather than on dealing with the details of service integration. It uses a very similar structure to JSON API, I think interestingly motivated by having similar goals, and both take similar principles to heart in terms of the dumb pipes idea. So there are some tools that I think everyone needs in order to build these little microclients for these little microservices. One, as I mentioned, is an HTTP client basis library that implements all of the boilerplate so that we don't have to, again, the example that I used was Faraday. I think it's a good one. I know there are others for other languages. Secondly, testing tools that provide mocking of the service so that you do not need to run an instance of it in order to test the client. Some great tools go a step further and record responses from the service. One in Ruby that I've used is called VCR. You run an instance of the service application, you run the tests from the client, the VCR gem records all the responses going in between, saves them as YAML files, and then you can have it replay them as the data being piped back into the HTTP client rather than actually talking to the server. Lastly, deployment mechanism. As I mentioned, I think it is important to build these tools as standalone libraries. There's great ways to integrate standalone libraries into the applications that we build, Ruby gems, NPM, package managers for other languages. GemFury is a service that allows you to have private repositories for all of those things. I know there are other ones. You can even use GitHub because many package managers allow you to pull, to specify repos to pull a library from and even use the GitHub version system. So in summary, I think the important things about microservices are to keep them simple by exposing idiomatic interfaces, including error handling, things that are familiar to the host environment and the programmers that will be working there, to set up tests that work in isolation so that work on the client library does not require work on the service or even caring too much about it. Organizing the project for unobtrusiveness in terms of integration, using existing dependency management tools rather than having some weird thing where it's in a lib directory somewhere. And to reuse familiar open API and open source conventions that leverage existing knowledge, such as using an existing basis API client rather than reinventing that, and using the emerging conventions from things like HAL and JSON API for defining the payloads that you return, or the payloads that you process. So to bring it back to what I characterized as the sort of point of this whole discussion, the point is to make it easy, and thus hopefully cheap, to extract parts of an application into a small service by minimizing the cognitive overhead for having to do so. We want to reduce the amount we need to think about. All of the points that I have made have been towards that goal. And what makes me really excited about all of this is it means minimizing the costs of trying new tools and trying new languages, which is something that I like to do. And that is the value of slim, efficient, if possibly, in some cases, compromised microclient libraries. And that's it. Thank you.